Over 4,500 years ago, human builders transported millions of tons of solid granite across the desert to construct the Great Pyramid of Giza. It stands as an enduring monument to absolute physical permanence. It also perfectly illustrates the fundamental logic behind human construction. We build from the top down. Our methodology relies entirely on centralized planning, precise blueprints, and the vast coordination of labor to force materials into shape. Fast forward to the modern era, and we've applied that same top-down logic to map the subatomic universe. Located 175 meters underground, the Large Hadron Collider utilizes massive superconducting magnets operating near absolute zero to smash particles together at nearly the speed of light. Look up, and you'll find the International Space Station, a 400-ton laboratory assembled piece by piece in low Earth orbit. It survives extreme radiation, microgravity, and massive temperature swings every single day. Humanity's mastery of the physical world relies entirely on conscious mathematical deliberation. Every bridge, skyscraper, and space station is an active, constant fight against environmental constraints. But that fight has a structural limit, known as the engineering bottleneck. This chart shows what happens when we try to scale our designs. While a building's physical height scales linearly, the energy and maintenance costs required to resist gravity and wind shear scale exponentially. Contrast that bottleneck with an entirely different approach. The largest living structure on Earth was built without a single blueprint, brain, or central planner. The Great Barrier Reef stretches for 2,300 kilometers and is clearly visible from space. It was constructed by the slow, collective accumulation of calcium carbonate, secreted layer by tiny, soft-bodied coral polyps over millennia. While human engineers build structures on the landscape, nature's bottom-up approach builds the landscape itself. It achieves a massive, sustainable scale that our top-down methods simply cannot match. This biological method of building is called stickmergy. Rather than following a master plan, complex structures emerge organically as thousands of individuals respond to local environmental cues left by others. Look at African termite mounds. In relative scale, these towering dirt columns are equivalent to human skyscrapers, reaching heights up to 20 feet. This diagram shows the mound's internal architecture, functioning as a living lung. It relies on complex internal chimneys. As wind passes over, the colony's metabolic heat causes warm air to rise and exhaust centrally, drawing cooler air in. Millions of blind insects maintain a perfectly stable, climate-controlled environment. They do this entirely through emergent behavior, drastically outperforming the energy efficiency of our conventional air conditioning systems. That same localized intelligence scales to handle massive logistics. In Brazil, scientists poured concrete into an abandoned ant nest and uncovered a sprawling subterranean megalopolis covering 500 square feet. To build it, the colony excavated 40 tons of soil. They organically mapped out specialized gardens, designated local nurseries, and optimized transport highways that perfectly mirror modern urban planning. This bottom-up engineering doesn't even require a nervous system. If we zoom into a single drop of seawater, we find single-celled algae called diatoms. These brainless organisms extract silica from the ocean to self-assemble perfectly geometric, high-porosity, glass-like shells. Their structural design naturally manages vibrations and prevents physical resonance. From vast subterranean ant highways to microscopic glass domes, nature's algorithms solve highly complex engineering problems using a fraction of the energy humans require. We are finally starting to pay attention. This is the frontier of biomimicry, using human scientific precision to actively replicate nature's structural efficiency. The Eastgate Center in Zimbabwe, for example, directly applies the passive cooling principles of the African termite mound. By mimicking that biological airflow, this massive commercial complex stays cool without using conventional air conditioning. We are even copying geometry to save material. The National Stadium in Beijing relies on the same Wozen lattice techniques utilized by weaver birds, achieving massive durability while using significantly less steel. Engineering excellence manifests in this deep integration, where a structure's very geometry manages its own internal climate and material load. Integrating our top-down scientific precision with these emergent biological algorithms offers a path toward a more efficient built environment. By adopting the logic of nature's architects, we can begin to design structures that share the same inherent resilience found in the natural systems that inspired them.